Tunguska explosion, the cosmic blast that shook Siberia on the morning of June 30, 1908. A remote region of Siberia, Russia, experienced an event so catastrophic, so unprecedented, that it would baffle scientists, historians, and enthusiasts for over a century in the isolated taiga forests near the Tunguska River. A massive explosion erupted with a force estimated to be between 10 and 50 megatons of TNT, equivalent to 1,000 times the power of the atomic bomb dropped on Hiroshima during World War II. The blast flattened over 2,000 square kilometers of ancient coniferous forest, toppling an estimated 80 million trees in a radial pattern outward from the epicenter. It shattered windows hundreds of kilometers away, shook the ground with the force of a magnitude 5 earthquake, and produced a shockwave that circled the earth twice. Yet, despite its immense power, the Tunguska explosion left no crater, no visible debris, and no clear explanation for its origin. For decades, this cosmic enigma has spawned countless theories, from the plausible to the fantastical, and it remains one of the most intriguing unsolved mysteries of the 20th century. To understand the Tunguska explosion is to journey into a world of scientific curiosity, historical serendipity, and cosmic wonder. A story that begins with the quiet dawn of a summer day in Siberia and continues to unfold as modern technology reveals new clues about one of the most powerful natural disasters in recorded history. To appreciate the full impact of the Tunguska explosion, one must first understand the setting in which it occurred. The Tunguska River flows through a remote stretch of the Siberian taiga, a vast forested region in northern Russia that is one of the least populated areas on Earth. In 1908, the area was inhabited primarily by the Evenki and Tungus peoples, indigenous groups who relied on hunting, reindeer herding, and fishing for their survival. These communities lived in small, scattered camps, far from major cities and modern infrastructure, and their way of life had remained largely unchanged for centuries. The taiga itself is a harsh, unforgiving environment, long, frigid winters with temperatures dropping to minus 40 degrees C, and short, humid summers where mosquitoes and other insects plague the land. The forests are dense with larch, pine, and spruce trees, many of which are hundreds of years old, and the terrain is dotted with marshes, rivers, and rocky outcrops. This isolation would prove crucial in the aftermath of the explosion. Because few people lived in the area, the loss of human life was minimal. But it also meant that the event went largely unreported for months, and scientific investigation was delayed for over a decade. When news of the blast finally reached the outside world, it was met with skepticism and confusion, as few could fathom a natural disaster of such magnitude occurring in a region so far from any known geological or volcanic activity. The first signs of the Tunguska explosion appeared shortly after 7, 00 a.m. local time on June 30, 1908. Eyewitnesses in the region later described a bright, fiery object streaking across the sky, moving from the southeast to the northwest. The object was visible for hundreds of kilometers, and its appearance was unlike anything the locals had ever seen. One Evenki herder named Seaman Semenov, who was approximately 65 kilometers from the epicenter, later recounted that the object was as bright as the sun, but much smaller and moving very fast. He described it as a fireball with a long, glowing tail that left a trail of smoke and dust in its wake. As the object approached the ground, it began to emit a series of loud, thunderous booms, which grew increasingly intense as it neared impact. Then, at approximately 7:17 a.m., a massive explosion occurred, sending a shockwave rippling outward in all directions. Semenov recalled being thrown to the ground by the force of the blast and feeling an intense heat that burned his face and hands. He later said that the sky turned black as night for several minutes, and that the air was filled with a thick, acrid smoke that smelled of sulfur and ash. Similar accounts were reported by other eyewitnesses across the region, from as far as 400 kilometers away. In the town of Vanavara, approximately 200 kilometers from the epicenter, residents reported that windows shattered, walls shook, and furniture was thrown across rooms. Some people were knocked off their feet, and many reported hearing a series of loud explosions that echoed for hours. Even in the city of Irkutsk, over 1,000 kilometers from the blast site, seismic stations recorded a disturbance that was initially mistaken for an earthquake. The shockwave from the explosion was so powerful that it traveled around the world, being detected by weather stations in Europe, North America, and Asia. In London, the barometric pressure dropped significantly, and in Washington, D.C., scientists at the Weather Bureau noted a sudden, unexplained fluctuation in atmospheric pressure. These distant observations would later prove crucial in estimating the size and power of the explosion. But at the time, they only added to the confusion surrounding the event. In the immediate aftermath of the explosion, the remote nature of the Tunguska region meant that little information about the event reached the outside world. The indigenous communities in the area were left to deal with the destruction on their own, as there was no way to contact authorities or receive assistance. The blast had destroyed reindeer herds, which were the primary source of food and livelihood for many Evenki and Tungus families, and the flattened forests made hunting and travel nearly impossible. Many of the local people believed that the explosion was a sign from the gods, a punishment for their sins, or the work of evil spirits. Some reported seeing strange lights in the sky in the days and weeks following the blast, and others claimed to have heard mysterious sounds coming from the forest. These stories, passed down through oral tradition, would later become an important source of information for scientists investigating the event, as they provided first-hand accounts of what happened on that fateful morning. However, It was not until several months later, when a Russian geologist named Leonid Kulik read a brief newspaper article about the explosion, that the first scientific interest in the Tunguska event was sparked. Kulik, who was working for the Russian Academy of Sciences at the time, was fascinated by the reports of a massive explosion in Siberia, and he began lobbying for an expedition to investigate the site. His efforts were initially met with resistance, as the Russian government was preoccupied with political and economic turmoil in the aftermath of the 1905 revolution, and funding for scientific expeditions was scarce. It was not until 1927, nearly 20 years after the explosion, that Kulik was finally able to lead the first official scientific expedition to the Tunguska site. Kulik's expedition was a grueling journey into one of the most remote and inhospitable regions of Siberia. The team traveled by train to Irkutsk, then by horse-drawn sleigh and reindeer caravan into the taiga. The journey took months, and the team faced extreme cold, hunger, and dangerous terrain. When they finally reached the area near the Podkamenea Tunguska River, they were greeted by a scene of utter devastation. For as far as the eye could see, the forest was flattened, with trees lying in a radial pattern, all pointing away from a central point. The trees were not just broken or uprooted. Many had been stripped of their branches and bark, and some had been completely charred by the intense heat of the explosion. Yet, to Kulik's surprise, there was no crater at the epicenter. This was one of the most puzzling aspects of the Tunguska event. A blast of such magnitude should have left a large, deep crater, similar to the craters left by meteor impacts elsewhere on Earth. But at Tunguska, there was nothing, no hole in the ground, no debris from a meteorite, no signs of an impact. Kulik and his team searched the area thoroughly, digging test pits and examining the soil and rock, but they found no evidence of a meteorite or any other extraterrestrial object. They did, however, find evidence of intense heat. The soil was baked and hardened, and some of the tree trunks had been fused together by the high temperatures. They also found small glassy spheres in the soil, which they believed were formed by the melting of rock and debris during the explosion. Despite these findings, Kulik was unable to determine the cause of the explosion, and his expedition returned to Moscow with more questions than answers. Kulik would lead 2 more expeditions to Tunguska in 1929 and 1939, but he was never able to find the crater or the source of the blast. He died in 1942 during World War II without solving the mystery of Tunguska. In the decades following Kulik's expeditions, the Tunguska explosion became a source of fascination for scientists around the world, and numerous theories were proposed to explain the event. The most widely accepted theory, and the one that has gained the most scientific support over time, is that the explosion was caused by the entry of a large meteoroid or comet into Earth's atmosphere. This theory, known as the meteoroid impact hypothesis, suggests that a celestial object estimated to be between 50 and 100 meters in diameter, entered the atmosphere at a high speed, approximately 20-30 kilometers per second, and exploded in the air, approximately 5-10 kilometers above the ground. The explosion would have been caused by the intense pressure and heat generated as the object pushed through the atmosphere, causing it to fragment and release its energy in a massive blast. This would explain why there is no crater. The object never actually reached the ground, but exploded in midair, with the force of the blast being directed downward and outward. The meteoroid impact hypothesis is supported by a number of key pieces of evidence. First, the radial pattern of the flattened trees is consistent with an airburst explosion, where the force of the blast radiates outward from a central point in the sky. Second, the glassy spheres found in the soil at the site are similar to tektites, which are formed when rock is melted by the heat of a meteor impact and then solidifies as it falls back to Earth. Third, the estimated energy of the explosion is consistent with the impact of a meteoroid of the size described. Finally, eyewitness accounts of a bright, fast-moving object in the sky prior to the explosion align with the entry of a meteoroid into the atmosphere. However, the meteoroid impact hypothesis is not without its flaws, and it has been challenged by a number of alternative theories over the years. One of the most persistent criticisms of the hypothesis is the lack of a crater and the absence of large amounts of meteorite debris. If a meteoroid of 5,100 meters in diameter exploded in the atmosphere, it should have left some fragments on the ground. But despite decades of searching, no significant meteorite debris has been found at the Tunguska site. Some scientists have suggested that the meteoroid was composed of ice or other volatile materials, which would have vaporized completely during the explosion, leaving no debris behind. This has led to the comet hypothesis, which proposes that the object was a small comet rather than a meteoroid. Comets are composed primarily of ice, dust, and rock, and if a comet entered the atmosphere, it would vaporize quickly, releasing a large amount of gas and dust, which would explain the lack of debris. The comet hypothesis also explains the bright tail reported by eyewitnesses, as comets often have tails of gas and dust when they are near the sun. However, the comet hypothesis also has its critics, who argue that comets are less dense than meteoroids and would not generate enough energy to cause an explosion of the magnitude seen at Tunguska. Additionally, comets are typically visible in the sky for weeks or months before they reach Earth. But there were no reports of a comet in the sky prior to the Tunguska explosion. Another alternative theory that gained popularity in the mid-20th century is the antimatter hypothesis. This theory suggests that the Tunguska explosion was caused by the collision of a small amount of antimatter with matter in Earth's atmosphere. Antimatter is a form of matter that is the opposite of normal matter. For every particle of matter, there is a corresponding antiparticle with the opposite charge. When matter and antimatter collide, they annihilate each other, releasing a massive amount of energy. Proponents of the antimatter hypothesis argue that a small amount of antimatter, approximately 100 grams, would be enough to generate the energy of the Tunguska explosion. They also note that the annihilation of antimatter would leave no debris, which would explain the lack of a crater and the absence of meteorite fragments. However, the antimatter hypothesis is highly unlikely, as antimatter is extremely rare in the universe, and there is no known natural process that would bring a significant amount of antimatter to Earth. Additionally, the annihilation of antimatter would produce a large amount of gamma radiation, which would have been detected by scientific instruments at the time. But there is no record of such radiation being observed in 1908. A more exotic theory proposed in the 1960s is the black hole hypothesis, which suggests that the Tunguska explosion was caused by a small black hole passing through Earth. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. A small black hole with a mass similar to that of a mountain would pass through Earth without leaving a crater, as it would simply pass through the planet's interior and exit on the other side. Proponents of this theory argue that the passage of a black hole through the atmosphere would generate a massive shockwave, which would explain the Tunguska explosion. However, this theory is also highly unlikely, as a small black hole passing through Earth would cause significant gravitational effects, such as earthquakes and tidal waves, which were not observed in 1908. Additionally, there is no evidence that a black hole passed through Earth at that time, and the theory is not supported by any scientific data. Other, more fringe theories have been proposed over the years, including the idea that the Tunguska explosion was caused by a UFO crash, a secret military experiment, or even a volcanic eruption. The UFO theory suggests that an extraterrestrial spacecraft crashed in the Tunguska region, causing the explosion. Proponents of this theory point to eyewitness accounts of a bright object in the sky and the lack of debris as evidence of a spacecraft. However, there is no scientific evidence to support this theory, and it is widely regarded as a pseudoscientific fantasy. The secret military experiment theory suggests that the explosion was caused by a test of a new weapon by the Russian government. But there is no evidence that such a weapon existed in 1908, and the Russian government has never claimed responsibility for the event. The volcanic eruption theory is also unlikely, as there are no active volcanoes in the Tunguska region, and the geological evidence does not support a volcanic origin for the explosion. Despite the lack of evidence for these fringe theories, they continue to capture the public imagination, and they are often featured in books, movies, and documentaries about the Tunguska explosion. In the 1950s and 1960s, advances in technology allowed scientists to conduct more detailed investigations of the Tunguska site, and new evidence emerged that supported the meteoroid impact hypothesis. In 1958, a team of Soviet scientists, led by Kirill Florensky, conducted an expedition to Tunguska, using new geophysical equipment to study the area. They found that the soil at the epicenter contained high levels of iridium, a rare metal that is found in meteorites, but is relatively rare in Earth's crust. This discovery was a major breakthrough, as it provided direct evidence of an extraterrestrial origin for the explosion. Iridium is often used as a fingerprint for meteor impacts, as it is abundant in meteorites and is deposited in the soil during an impact event. The Florensky team also found that the glassy spheres in the soil contained high levels of nickel and iron, which are also common in meteorites. These findings strongly supported the idea that the Tunguska explosion was caused by a meteoroid impact. In the 1970s, another team of scientists, led by Viktor Zolotov, conducted further studies of the Tunguska site, using satellite imagery and aerial surveys to map the area. They found that the flattened forest formed a perfect circle with a diameter of approximately 50 kilometers, which is consistent with an airburst explosion. They also found that the trees at the epicenter were completely stripped of their branches and bark, which is evidence of intense heat and pressure from the blast. These studies helped to solidify the meteoroid impact hypothesis as the most likely explanation for the Tunguska explosion in the 1980s and 1990s. Advances in computer modeling and forensic science allowed scientists to simulate the Tunguska explosion and test different scenarios. Using data from eyewitness accounts, geological evidence, and atmospheric measurements, scientists were able to create detailed models of the event. These models showed that a meteoroid of approximately 60 meters in diameter, traveling at a speed of 25 kilometers per second, would explode in the atmosphere at an altitude of approximately 8 kilometers, generating a blast wave with a force of 15 megatons of TNT. This simulation matched the observed damage at the Tunguska site, including the radial pattern of the flattened trees, the extent of the destruction, and the shockwave that circled the Earth. The models also explained why there was no crater. The meteoroid fragmented and vaporized before reaching the ground, so there was no impact with the Earth's surface. Additionally, the models showed that the heat from the explosion would have melted the surrounding rock and soil, forming the glassy spheres found at the site. These simulations provided strong support for the meteoroid impact hypothesis, and they helped to dismiss many of the alternative theories. Despite the growing support for the meteoroid impact hypothesis, there are still some unanswered questions about the Tunguska explosion. One of the most puzzling questions is why no large meteorite fragments have been found at the site. If a 60-meter meteoroid exploded in the atmosphere, it should have left some fragments on the ground, even if most of it vaporized. Some scientists have suggested that the meteoroid was composed of a porous, fragile material, such as chondrite, which would have fragmented into small pieces that were scattered over a large area and buried by the forest debris. Others have suggested that the fragments were carried away by glaciers or washed away by rivers in the decades following the explosion. In recent years, scientists have used metal detectors and ground-penetrating radar to search for meteorite fragments at the Tunguska site. But so far, no significant fragments have been found. This remains one of the biggest mysteries of the Tunguska event, and it continues to fuel speculation about alternative theories. Another unanswered question is the exact composition of the meteoroid. Was it a stony meteorite, an iron meteorite, or a comet? Most scientists believe that it was a stony meteorite, as stony meteorites are the most common type of meteorite and are more likely to explode in the atmosphere than iron meteorites, which are denser and more likely to reach the ground. However, some scientists have suggested that it could have been a comet, as comets are composed of ice and dust and would vaporize completely during an explosion, leaving no debris. To resolve this question, scientists have analyzed the glassy spheres found at the Tunguska site. The composition of these spheres provides clues about the composition of the meteoroid. Studies have shown that the spheres contain high levels of silicates, which are common in stony meteorites, but they also contain traces of water and organic compounds, which are more common in comets. This has led some scientists to propose that the meteoroid was a cometary meteoroid, a fragment of a comet that had broken off and entered the atmosphere. This hypothesis would explain both the presence of silicates from the rocky part of the comet and water and organic compounds from the icy part of the comet. However, more research is needed to confirm this hypothesis. In addition to the scientific mysteries surrounding the Tunguska explosion, the event also has a rich cultural and historical legacy. For the indigenous peoples of the Tunguska region, the explosion was a life-changing event that altered their way of life forever. The destruction of reindeer herds and the flattening of the forest made it difficult for them to survive in the area, and many were forced to relocate to other regions. The event also became a part of their oral tradition, with stories of the fire in the sky being passed down from generation to generation. These stories have provided valuable insights into the event, as they offer first-hand accounts of what happened on that fateful morning. For the Russian people, the Tunguska explosion became a symbol of the country's vast and mysterious wilderness, and it captured the imagination of writers, artists, and scientists. The Soviet Union, the Tunguska event was often used as a symbol of scientific progress, as it represented the power of human curiosity and the ability to solve even the most complex mysteries. Today, the Tunguska explosion is a popular tourist destination, with hundreds of people visiting the site each year to see the flattened forest and learn about the event. The Russian government has also established a nature reserve in the area to protect the site and promote scientific research. The Tunguska explosion has also had a significant impact on the field of planetary science. It was one of the first events to highlight the danger posed by near-Earth objects, NEO, asteroids, comets, and other celestial bodies that orbit the Sun and could potentially collide with Earth. Before the Tunguska event, scientists paid little attention to the threat of NEO impacts, but the explosion showed that even a relatively small NEO could cause massive destruction if it collides with Earth. Today, scientists around the world are working to identify and track NEOs in order to predict and prevent future impacts. The Tunguska explosion is often used as a case study in these efforts, as it demonstrates the potential consequences of an NEO impact and the importance of early detection. In 1998, the United Nations established the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG, to coordinate global efforts to detect and respond to NEO threats. These organizations work with scientists and governments around the world to monitor NEOs and develop strategies to deflect or destroy any objects that pose a threat to Earth. The Tunguska explosion, therefore, has had a lasting impact on our understanding of the universe and our ability to protect our planet from cosmic threats. In recent years, new technologies have allowed scientists to conduct even more detailed investigations of the Tunguska site. In 2007, a team of scientists from the University of Bologna in Italy used ground-penetrating radar to search for evidence of a subsurface crater at the Tunguska epicenter. They found a circular structure approximately 100 meters in diameter, which they believe could be the remains of a small crater caused by the explosion. However, other scientists have disputed this finding, arguing that the structure is a natural geological formation. In 2013, another team of scientists, led by Andrei Zlobin of the Russian Academy of Sciences, announced that they had found small fragments of a meteorite at the Tunguska site. The fragments, which were approximately 1 millimeter in size, were found in the soil at the epicenter and contained high levels of iridium and other elements consistent with a meteorite. This discovery was a major breakthrough, as it provided the first concrete evidence of meteorite debris at the Tunguska site. However, some scientists have questioned the authenticity of the fragments, arguing that they could have been contaminated by meteorite debris from other sources. Despite these controversies, the discovery has reignited interest in the Tunguska explosion and has led to new research into the event. Another recent development in the study of the Tunguska explosion is the use of satellite imagery to map the area. In 2018, a team of scientists from the Russian Academy of Sciences used high-resolution satellite imagery to create a detailed map of the Tunguska site. The map showed that the flattened forest forms a series of concentric circles, which is consistent with an airburst explosion. The scientists also found that the trees in the innermost circle were completely destroyed, while the trees in the outer circles were only partially damaged, which aligns with the expected pattern of an airburst. The satellite imagery also revealed new details about the extent of the destruction, including areas that had not been previously mapped. This research has helped to refine our understanding of the Tunguska explosion and has provided new evidence to support the meteoroid impact hypothesis. Despite the progress that has been made in understanding the Tunguska explosion, there are still many questions that remain unanswered. For example, why did the meteoroid explode in the atmosphere instead of reaching the ground? What was the exact size and composition of the meteoroid? Why have no large meteorite fragments been found at the site? These questions continue to challenge scientists, and they are the subject of ongoing research. In the coming years, new technologies, such as improved satellite imagery, advanced forensic techniques, and better computer models, will likely provide new insights into the Tunguska event. It is possible that we will one day have a complete understanding of what happened on that summer morning in 1908. But for now, the Tunguska explosion remains one of the most intriguing unsolved mysteries of the cosmos. To fully appreciate the significance of the Tunguska explosion, it is important to consider it in the context of Earth's history. Throughout the planet's 4.5 billion year history, there have been numerous large impacts by asteroids and comets. The most famous of these is the impact that occurred 66 million years ago, which led to the extinction of the dinosaurs. That impact was caused by an asteroid approximately 10 kilometers in diameter, which created a crater 180 kilometers in diameter in what is now the Yucatan Peninsula of Mexico. The Tunguska explosion was much smaller than this, but it is still one of the largest impacts in recorded human history. It serves as a reminder that Earth is not immune to cosmic threats, and that even a relatively small NEO can cause massive destruction. The Tunguska event also highlights the importance of scientific research and international cooperation in understanding and mitigating these threats. By studying the Tunguska explosion, we can learn more about the nature of NEOs, their behavior when they enter Earth's atmosphere, and the potential consequences of future impacts. The Tunguska explosion also has a profound impact on our understanding of the universe. It is a reminder that we live in a dynamic, ever-changing cosmos where celestial events can have a significant impact on our planet. The event has inspired generations of scientists to study astronomy, geology, and planetary science, and it has led to numerous advancements in these fields. It has also captured the public imagination, inspiring books, movies, and documentaries that explore the mystery of the explosion and its implications for our planet. From science fiction novels that imagine a future where Earth is threatened by a similar event, to documentaries that explore the scientific evidence and theories surrounding Tunguska, the event has become a part of popular culture. It is a symbol of the unknown, a reminder that there are still many mysteries in the universe waiting to be solved. In conclusion, the Tunguska explosion of 1908 was one of the most powerful and mysterious natural disasters in recorded history. It flattened over 2,000 square kilometers of Siberian taiga, shook the ground with the force of an earthquake, and produced a shockwave that circled the Earth twice. For over a century, scientists have debated the cause of the explosion, with the meteoroid impact hypothesis emerging as the most likely explanation, while there are still unanswered questions about the event. Advances in technology and scientific research have provided valuable insights into what happened on that fateful morning. The Tunguska explosion has had a lasting impact on our understanding of the universe, our planet, and the threats posed by near-Earth objects. It serves as a reminder of the power of nature, the importance of scientific curiosity, and the need to protect our planet from cosmic dangers. As we continue to study the Tunguska event, we move closer to solving one of the greatest mysteries of the 20th century, and we gain a better understanding of our place in the cosmos. The Tunguska explosion may have occurred over a century ago, but its legacy continues to shape our world today, inspiring scientists and enthusiasts alike to explore the unknown and seek the truth. To delve deeper into the Tunguska explosion, it is essential to examine the eyewitness accounts in greater detail, as they provide the most direct evidence of the event. The stories of the Evenki and Tungus peoples, as well as Russian settlers and explorers in the region, offer a vivid picture of what happened on June 30, 1908. One of the most detailed accounts comes from Seaman Semenov, who was herding reindeer near the village of Vanavara, approximately 65 kilometers from the epicenter. Semenov later told investigators that he was sitting outside his tent when he saw a bright object in the sky, moving from the southeast to the northwest. He described the object as a large fireball, brighter than the sun, with a long, glowing tail. As the object approached, it began to emit a series of loud, thunderous booms, which grew increasingly intense. Then, at approximately 7:17 a.m., he felt a powerful shockwave that threw him to the ground. He recalled that the sky turned black, and that he could smell a strong, acrid odor, like sulfur. When he stood up, he saw that the forest around him was shaking, and that trees were falling in the distance. Another eyewitness, a Russian settler named Ivan Kulesh, who was approximately 100 kilometers from the epicenter, reported seeing a pillar of fire rising into the sky after the explosion. He said that the pillar was so bright that it illuminated the entire area, and that it remained visible for several hours. He also reported that the ground shook violently, and that windows in his house shattered. Similar accounts were reported by other settlers and indigenous people across the region, from as far as 400 kilometers away. These eyewitness accounts are crucial, as they provide a timeline of the event and describe the physical characteristics of the explosion, such as the bright object, the shockwave, and the pillar of fire. Another important source of information about the Tunguska explosion is the scientific data collected in the aftermath of the event. Seismic stations around the world recorded the shockwave from the explosion, which allowed scientists to estimate the magnitude and location of the blast. In Irkutsk, Russia, a seismic station recorded a disturbance at 7:17 a.m. local time, which was initially mistaken for an earthquake. The shockwave was also detected by weather stations in Europe, North America, and Asia, which recorded sudden changes in atmospheric pressure. In London, the barometric pressure dropped by 1.5 millibars, and in Washington, D.C., scientists at the Weather Bureau noted a similar drop. These measurements allowed scientists to calculate the energy of the explosion, which is estimated to be between 10 and 50 megatons of TNT. This energy estimate is based on the size of the shockwave and the extent of the destruction at the Tunguska site. Additionally, scientists have studied the tree rings of the trees in the Tunguska region to determine the impact of the explosion on the environment. Tree rings can provide information about the amount of radiation, temperature, and precipitation in a given year, and they can also show signs of stress caused by natural disasters. Studies of tree rings from the Tunguska region have shown that the trees experienced significant stress in 1908, which is consistent with the heat and pressure from the explosion. The tree rings also show that the trees in the area grew more slowly in the years following the explosion, which suggests that the environment was damaged by the blast. The geological evidence at the Tunguska site also provides valuable insights into the explosion. The most striking feature of the site is the radial pattern of the flattened trees, which all point away from the epicenter. This pattern is consistent with an airburst explosion, where the force of the blast radiates outward from a central point in the sky. The trees at the epicenter are completely stripped of their branches and bark, and many are charred, which is evidence of intense heat. The soil at the epicenter is baked and hardened, and it contains high levels of iridium, a rare metal that is found in meteorites. The glassy spheres found in the soil are another important piece of geological evidence. These spheres are approximately 15 millimeters in diameter, and they are composed of silicates, nickel, and iron. They are believed to have been formed when the heat from the explosion melted the surrounding rock and soil, which then solidified as it fell back to Earth. These spheres are similar to tektites, which are formed by meteor impacts, and they provide strong evidence of an extraterrestrial origin for the explosion. Over the years, numerous expeditions have been conducted to the Tunguska site, each bringing new insights and discoveries. The first expedition, led by Leonid Kulik in 1927, was a landmark event, as it was the first time scientists had visited the site to study the explosion. Kulik and his team spent months in the taiga, mapping the area and collecting samples. They found the radial pattern of the flattened trees, the baked soil, and the glassy spheres, but they were unable to find a crater or any meteorite debris. Kulik's expeditions laid the groundwork for future research, and they helped to bring the Tunguska explosion to the attention of the scientific community. In the 1950s, and 1960s, Soviet scientists conducted more detailed expeditions using new technology to study the site. They found high levels of iridium in the soil, which provided direct evidence of an extraterrestrial origin. In the 1970s and 1980s, international teams of scientists began to study the Tunguska site, bringing new perspectives and techniques. These teams used satellite imagery, aerial surveys, and ground-penetrating radar to map the area and search for evidence. In recent years, advances in technology have allowed scientists to conduct even more detailed research, including DNA analysis of the soil and tree samples, and high-resolution imaging of the site. These studies have helped to refine our understanding of the Tunguska explosion and have provided new evidence to support the meteoroid impact hypothesis. Despite the overwhelming evidence supporting the meteoroid impact hypothesis, there are still some scientists who argue for alternative theories. One of the most prominent alternative theories is the comet hypothesis, which suggests that the Tunguska explosion was caused by a small comet. Comets are composed primarily of ice, dust, and rock, and they have a tail of gas and dust when they are near the sun. Proponents of the comet hypothesis argue that a comet entering the atmosphere would vaporize quickly, releasing a large amount of gas and dust, which would explain the lack of debris at the Tunguska site. They also note that the eyewitness accounts of a bright object with a tail are consistent with a comet. However, there are several problems with the comet hypothesis. First, comets are less dense than meteoroids, so they would not generate enough energy to cause an explosion of the magnitude seen at Tunguska. Second, comets are typically visible in the sky for weeks or months before they reach Earth, but there were no reports of a comet in the sky prior to the Tunguska explosion. Third, the glassy spheres found at the Tunguska site contain high levels of silicates, which are more common in meteorites than in comets. Despite these problems, the comet hypothesis continues to be debated by some scientists, and it remains a possible explanation for the Tunguska explosion. Another alternative theory that has been proposed is the asteroid impact hypothesis, which is similar to the meteoroid impact hypothesis, but suggests that the object was a larger asteroid. Proponents of this theory argue that the object was between 100 and 200 meters in diameter, and that it exploded in the atmosphere with a force of 50 megatons of TNT. They suggest that the asteroid was composed of iron, which would have allowed it to survive longer in the atmosphere before exploding. However, there is no evidence of iron meteorite debris at the Tunguska site, which would be expected if the object was an iron asteroid. Additionally, the radial pattern of the flattened trees is consistent with a smaller object exploding at a higher altitude, which aligns with the meteoroid impact hypothesis. The asteroid impact hypothesis is therefore less likely than the meteoroid impact hypothesis, but it remains a possible explanation. The antimatter hypothesis and the black hole hypothesis are two other alternative theories that have been proposed, but they are widely regarded as unlikely. The antimatter hypothesis suggests that the explosion was caused by the collision of a small amount of antimatter with matter in Earth's atmosphere. However, antimatter is extremely rare in the universe, and there is no known natural process that would bring a significant amount of antimatter to Earth. The black hole hypothesis suggests that the explosion was caused by a small black hole passing through Earth, but there is no evidence that a black hole passed through Earth in 1908, and the theory is not supported by any scientific data. These theories are therefore considered to be pseudoscientific and are not taken seriously by most scientists. The Tunguska explosion has also had a significant impact on popular culture. It has inspired numerous books, movies, and documentaries, which explore the mystery of the event and its implications for our planet. One of the most famous books about the Tunguska explosion is The Tunguska Fireball by Roy Gallant, which provides a detailed account of the event and the scientific research surrounding it. The book was first published in 1995 and has been updated several times to include new discoveries. Another popular book is Tunguska, The Great Siberian Mystery by Ivanov and Zolotov, which is written by two Russian scientists who have conducted extensive research on the Tunguska site. The book provides a detailed analysis of the geological and scientific evidence, and it argues in favor of the meteoroid impact hypothesis. In addition to books, the Tunguska explosion has been featured in numerous movies and documentaries. One of the most popular documentaries is Tunguska, The Mystery Exploded, which was produced by the BBC in 2000. The documentary features interviews with scientists and eyewitnesses, and it explores the various theories about the explosion. It also includes reenactments of the event, which help to bring the story to life. The Tunguska explosion has also been featured in science fiction movies, such as The Day the Earth Caught Fire and Armageddon, which imagine a future where Earth is threatened by a similar event. The Tunguska explosion has also become a popular subject of speculation and conspiracy theories. Some people believe that the explosion was caused by a UFO crash, while others believe that it was a secret military experiment. These conspiracy theories are not supported by any scientific evidence, but they continue to capture the public imagination. One of the most popular conspiracy theories is that the Tunguska explosion was caused by a test of a nuclear weapon by the Russian government. However, there is no evidence that the Russian government had nuclear weapons in 1908, and the technology to develop such weapons did not exist at the time. Another conspiracy theory is that the explosion was caused by a collision with a planetoid or a fragment of a dead star. This theory is also not supported by any scientific evidence, and it is widely regarded as a fantasy. Despite the lack of evidence for these conspiracy theories, they continue to be spread online and in popular culture, which can make it difficult for the public to separate fact from fiction. In recent years, there has been a renewed interest in the Tunguska explosion, thanks in part to advances in technology and the discovery of new evidence. In 2013, a team of scientists led by Andrei Zilobin announced that they had found small fragments of a meteorite at the Tunguska site. The fragments were found in the soil at the epicenter, and they contained high levels of iridium and other elements consistent with a meteorite. This discovery was a major breakthrough, as it provided the first concrete evidence of meteorite debris at the Tunguska site. However, some scientists have questioned the authenticity of the fragments, arguing that they could have been contaminated by meteorite debris from other sources. To resolve this controversy, further research is needed to analyze the fragments and confirm their origin. In 2018, a team of scientists from the Russian Academy of Sciences used high-resolution satellite imagery to create a detailed map of the Tunguska site. The map showed that the flattened forest forms a series of concentric circles, which is consistent with an airburst explosion. The scientists also found that the trees in the innermost circle were completely destroyed, while the trees in the outer circles were only partially damaged, which aligns with the expected pattern of an airburst. This research has helped to refine our understanding of the Tunguska explosion and has provided new evidence to support the meteoroid impact hypothesis. Another recent development in the study of the Tunguska explosion is the use of computer modeling to simulate the event. Scientists have used data from eyewitness accounts, geological evidence, and atmospheric measurements to create detailed models of the explosion. These models show that a meteoroid of approximately 60 meters in diameter, traveling at a speed of 25 kilometers per second, would explode in the atmosphere at an altitude of approximately 8 kilometers, generating a blast wave with a force of 15 megatons of TNT. This simulation matches the observed damage at the Tunguska site, including the radial pattern of the flattened trees, the extent of the destruction, and the shockwave that circled the Earth. The models also explain why there was no crater. The meteoroid fragmented and vaporized before reaching the ground, so there was no impact with the Earth's surface. Additionally, the models show that the heat from the explosion would have melted the surrounding rock and soil, forming the glassy spheres found at the site. These simulations provide strong support for the meteoroid impact hypothesis, and they help to dismiss many of the alternative theories. Despite the progress that has been made in understanding the Tunguska explosion, there are still many questions that remain unanswered. For example, why did the meteoroid explode in the atmosphere instead of reaching the ground? What was the exact size and composition of the meteoroid? Why have no large meteorite fragments been found at the site? These questions continue to challenge scientists, and they are the subject of ongoing research. In the coming years, new technologies, such as improved satellite imagery, advanced forensic techniques, and better computer models, will likely provide new insights into the Tunguska event. It is possible that we will one day have a complete understanding of what happened on that summer morning in 1908. But for now, the Tunguska explosion remains one of the most intriguing unsolved mysteries of the cosmos. The Tunguska explosion is also an important reminder of the need to protect our planet from near-Earth objects. While the Tunguska event did not cause significant human casualties, it showed that even a relatively small NEO can cause massive destruction. Today, scientists around the world are working to identify and track NEOs in order to predict and prevent future impacts. The International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG, coordinate global efforts to detect and respond to NEO threats. These organizations work with scientists and governments around the world to monitor NEOs and develop strategies to deflect or destroy any objects that pose a threat to Earth. The Tunguska explosion, therefore, has had a lasting impact on our understanding of the universe and our ability to protect our planet from cosmic threats, in addition to its scientific and practical significance. The Tunguska explosion also has a profound cultural and spiritual significance. For the indigenous peoples of the Tunguska region, the event was a sacred and transformative experience. It was seen as a message from the spirits, a reminder of the power of nature, and a call to respect the land. The stories and traditions surrounding the Tunguska explosion have been passed down from generation to generation, and they continue to shape the culture and identity of these communities. For the scientific community, the Tunguska explosion is a symbol of the power of human curiosity and the importance of scientific research. It has inspired generations of scientists to study astronomy, geology, and planetary science, and it has led to numerous advancements in these fields. For the general public, the Tunguska explosion is a source of wonder and fascination, a reminder that there are still many mysteries in the universe waiting to be solved. As we look to the future, the study of the Tunguska explosion will continue to be a priority for scientists around the world. New technologies and techniques will allow us to conduct more detailed research, and we will likely uncover new evidence that will help to solve the remaining mysteries of the event. The Tunguska explosion is a testament to the power of nature, the complexity of the universe, and the resilience of the human spirit. It is a story that has captivated the world for over a century, and it will continue to inspire and intrigue us for generations to come. Whether we are scientists, historians, or simply curious individuals, the Tunguska explosion reminds us that the universe is full of surprises and that there is always more to learn. To further explore the Tunguska explosion, it is important to consider the impact of the event on the environment. The explosion flattened over 2,000 square kilometers of forest, which had a significant impact on the local ecosystem. The loss of trees led to soil erosion, and the heat from the explosion killed a large number of plants and animals. However, the taiga is a resilient ecosystem, and over time, the forest has begun to recover. Today, the Tunguska site is covered with young trees, and the ecosystem has largely returned to its pre-explosion state. This recovery is a testament to the resilience of nature, and it provides valuable insights into how ecosystems can recover from major disasters. The recovery of the Tunguska forest also highlights the importance of protecting natural ecosystems, as they are able to adapt and recover from even the most catastrophic events. Another important aspect of the Tunguska explosion is its impact on climate. The explosion released a large amount of dust and gas into the atmosphere, which could have had a temporary impact on global climate. Some scientists have suggested that the dust and gas from the explosion blocked sunlight, leading to a slight cooling of the Earth's surface. However, there is no clear evidence of a significant climate change following the Tunguska explosion. Studies of historical weather data show that there was no significant cooling in the years following 1908, which suggests that the impact of the explosion on climate was minimal. This is likely because the amount of dust and gas released by the explosion was relatively small compared to other major volcanic eruptions, which can release large amounts of ash and gas into the atmosphere and cause significant climate change. Despite this, the Tunguska explosion provides a valuable case study for understanding how large-scale events can impact the Earth's climate. The Tunguska explosion also has implications for the search for extraterrestrial life. While the event itself was caused by a natural celestial object, it highlights the possibility of other cosmic events that could impact life on Earth. For example, if a large asteroid or comet were to collide with Earth, it could cause a mass extinction event, similar to the one that killed the dinosaurs. This has led scientists to consider the possibility of life on other planets and how they might be affected by similar cosmic events. The Tunguska explosion also reminds us that Earth is a fragile planet and that we need to take steps to protect it from cosmic threats. This includes monitoring near-Earth objects, developing strategies to deflect or destroy them, and reducing our impact on the environment. In recent years, there has been a growing interest in the Tunguska explosion among amateur scientists and enthusiasts. Many people have formed online groups and forums to discuss the event, share theories, and conduct their own research. These amateur researchers have made valuable contributions to the study of the Tunguska explosion, often bringing new perspectives and ideas to the table. For example, some amateur researchers have used satellite imagery and other online tools to map the Tunguska site and search for new evidence. Others have conducted experiments to simulate the explosion and test different theories. While these amateur efforts are not always rigorous from a scientific standpoint, they have helped to keep the Tunguska explosion in the public eye and have inspired new research. The Tunguska explosion is also a reminder of the importance of scientific collaboration. Over the years, scientists from around the world have worked together to study the event, sharing data, techniques, and ideas. This collaboration has been crucial in advancing our understanding of the Tunguska explosion, and it has led to numerous breakthroughs. For example, the discovery of iridium in the soil at the Tunguska site was the result of collaboration between Soviet and international scientists. Similarly, the computer models used to simulate the explosion were developed by scientists from multiple countries. This collaboration highlights the importance of international cooperation in scientific research, and it serves as a model for how scientists can work together to solve complex problems. In conclusion, the Tunguska explosion of 1908 is a fascinating and complex event that has captivated scientists and the public alike for over a century. It was a massive cosmic blast that flattened thousands of square kilometers of Siberian taiga, shook the earth, and left a trail of mystery and speculation. While the meteoroid impact hypothesis is the most widely accepted explanation for the event, there are still many unanswered questions that continue to challenge scientists. The Tunguska explosion has had a lasting impact on our understanding of the universe, our planet, and the threats posed by near-Earth objects. It has inspired scientific research, cultural expression, and public curiosity, and it remains one of the most intriguing unsolved mysteries of the 20th century. As we continue to study the Tunguska event, we move closer to solving its mysteries and gaining a better understanding of our place in the cosmos. The Tunguska explosion is a reminder that the universe is full of wonders and surprises, and that there is always more to learn. To fully grasp the significance of the Tunguska explosion, it is important to place it in the context of other major cosmic events that have impacted Earth. Throughout history, Earth has been struck by numerous asteroids and comets, each with varying degrees of impact. The most famous of these is the Chicxulub impact, which occurred 66 million years ago and led to the extinction of the dinosaurs. This impact was caused by an asteroid approximately 10 kilometers in diameter, which created a crater 180 kilometers in diameter and released an estimated 100 trillion tons of TNT equivalent energy. The Tunguska explosion was much smaller than this, but it is still one of the largest impacts in recorded human history. It serves as a reminder that even a relatively small near-Earth object can cause massive destruction if it collides with Earth. The Tunguska event also highlights the importance of studying these events, as they can provide valuable insights into the history of our planet and the threats we face from the cosmos. Another important context for the Tunguska explosion is the development of planetary defense. In recent years, there has been a growing awareness of the threat posed by near-Earth objects, and governments around the world have begun to invest in planetary defense programs. These programs aim to identify and track near-Earth objects and to develop strategies to deflect or destroy any objects that pose a threat to Earth. The Tunguska explosion is often used as a case study in these programs, as it demonstrates the potential consequences of an unforeseen impact. For example, the International Asteroid Warning Network, IAWN, uses data from the Tunguska explosion to improve its ability to detect and respond to near-Earth objects. The Tunguska event also serves as a reminder of the importance of early detection, as it is much easier to deflect a small object than a large one. By studying the Tunguska explosion, we can learn how to better protect our planet from future cosmic threats. The Tunguska explosion also has implications for the field of astrophysics. It provides a unique opportunity to study the behavior of a meteoroid entering Earth's atmosphere and exploding in midair. This information is valuable for understanding the physics of cosmic impacts and for developing models of how near-Earth objects behave when they enter our atmosphere. The Tunguska event also provides insights into the composition of meteoroids and comets, which can help scientists to better understand the formation and evolution of the solar system. For example, the glassy spheres found at the Tunguska site provide information about the composition of the meteoroid, which can help scientists to determine its origin and history. This information is crucial for understanding the formation of the solar system and the role that meteoroids and comets played in its evolution. In addition to its scientific implications, the Tunguska explosion also has a cultural and historical significance that cannot be overstated. It has become a symbol of the unknown, a reminder that there are still many mysteries in the universe waiting to be solved. It has inspired writers, artists, and scientists to explore the boundaries of human knowledge and to push the limits of what we know about the cosmos.